First I just wanted to talk to you about what the Rubik's Cube is made of. So there's 8 corner cublets, you can see them here. They're on the corners of the cube. There's 12 edge cublets, so they're these ones here. And there's 6 center cublets, which are these ones in the center of each of the faces. And these center ones are fixed. They don't move because they're connected to the middle of the cube, which has these axes which keep it in place. You could probably notice that the 8 corner cublets represent the 8 vertices of the cube, the 12 edge cublets are the 12 edges, and the 6 center cublets are 6 faces. So there's a little bit of notation as well for the Rubik's Cube. We can label each of the faces to make describing moves more convenient. That would be F for the front face and B for the back face, L for the left face and R for the right face, and U for the up face and D for the down face. And that's just to avoid confusion between the bottom and back faces. So we call them up and down, U and D instead. So we use the notation for the faces to represent rotations clockwise and anti-clockwise as well. So D represents a rotation of the bottom face, down face, 90 degrees clockwise, and D to the -1 represents the opposite, so the rotation anti-clockwise. D squared represents doing D twice, so that's rotating 90 degrees clockwise twice, so that's 180 degrees clockwise. And if you put 2 moves next to each other, that just represents doing the first move followed by the next move. So that would be a rotation of the front face and then the rotation of the left face, anti-clockwise. Okay, the first thing we can do with the Rubik's Cube is try and calculate how many different states you can have the Rubik's Cube in. And to do that, we can consider arranging the corner and edge pieces because the center cublets don't move. So, does anyone have any idea how many ways there are to arrange each of the 8 corner cublets? Any ideas? Yep.
Would it be 8 factorial amount, or?
So there would be 8 factorial, and that's the number of ways to place each of the corner cublets in one of the 8 corner positions, right? But there's something else we can also consider, and that is the faces of the cube. So the faces of each of the small cublets, they have 3 coloured faces. So we could arrange each of these corner cublets in 3 different ways, because they will have 3 different colours. So they can have red on top, green there, and white there, or we can swap it around so it's white on top and green and red on top.
I was just wondering about that. So I know if you have like a corner cube, say you have like a solved cube,
right.
If a corner piece is twisted, you can't actually solve it back, but if 2 are twisted, you can solve it back. So does that account for if only 1 is? Or
yes, that will, but we'll come to that at the end.
Okay.
Right. And the same for the 12 edge pieces. There's 12 factorial ways of arranging them in each of the positions, and because each edge piece has 2 faces, you times that by 2. And we will come back to whether or not a Rubik's Cube can be solved if some of the corner cublets or edge pieces are in a different arrangement. So here we go. It's impossible to rotate 1 corner cublet by itself, and it's impossible to flip 1 edge cublet by itself, and to swap the positions of 2 cublets only. And so each of these correspond to dividing the total by a certain amount. So because you can't rotate a single corner cublet, that means only one of the for every set of 8 cublets, you can only have one of those rotations of those cublets will be correct. So we divide the total by 3, because only one of the arrangements for each of the corner arrangements, only a third of them are possible. The same here, we divide by 2. And at the end here, we can only have cubelets with the same position. You can't swap 2 over. So that means half of the possibilities that we thought of before aren't possible. So that'll be divided by 2 again. It might be a bit clearer if I show you on the cube. If I can get that up. I don't know if you can see.
You need to alt-tab it.
If you can see this. Right. There you go. If we just scramble it a bit. I don't know if you can see. There you go. Okay. If we were to rotate this cubelet either left or right, then this cube would be solvable. And if you rotate it the other direction, that would be the same. So only a third of the possible combinations and arrangements of the cubelets would work. Same for the edge cubelets. If we flip this edge cublet around to the reds that side and the greens that side, this cube wouldn't be solvable. So that's why we divide by 3, 2 and 2 in there, bottom. So that means our total is what we got before. Oh, so and before, also, because we've got 8 corner cubelets, we have to put 3 to the power of 8. So that's the positions of each of the separate cubelets. And the same here, 2 to the power of 12. And that's where we get this number from. 43 quintillion something, I think. And that's 4.3 times 10 to 19. Right. So the Rubik's Cube and its permutations are very closely linked to group theory, and that's the study of sets and binary operations. Does anyone know what a set or a binary operation is? No, I think this might be something new. Yeah. So a set is just a collection of distinct objects. That might be numbers or cats, anything really. But in this sense, it's the collection of moves you can do on the Rubik's Cube. And a binary operation is an operation on a set where you combine 2 elements from that set and you produce another element of that set. So that might not make a lot of sense now, but we'll cover that again later on. So a group consists of a set and a binary operation together. And in order for a set and a binary operation to be called a group, it has to satisfy 4 axioms of a group, and we'll get into that now. Okay. And we will look at each of these with the set of integers. I don't know if any of you have seen that notation before. Z. That represents the set of integers. Okay. And that's obviously addition. You've all seen that before. Okay. Right. So the first axiom is closure, and this is what we were talking about before. So saying that a group is closed is equivalent to saying that the operation of the group is binary on that set. So for the example of integers and addition, if we were to take 2 elements from the integers, so for example let's say 2 and 3, under addition, if we add these together, we get 5, which is another integer, and that will work for any integers. If you add 2 integers together, you always get another integer, or another element of the integer set. And that's what closure means there. Identity. So what this here is saying is each group must have an identity element, and we call that E, that exists in the group, in the set, such that for all A in G, so that basically means for all the elements in the set, that A star E is equal to E star A is equal to A. And this here is just what we use to replace plus or minus or divide or times or whatever. Then that's just the symbol to represent the operation. So this here says that there must be an element in this set that if you add it or multiply it or subtract it, you get the same thing back. So A, when you operate E on A, you get A back, and that's the same if you do it the opposite way around. E star A is A. And the example with integers and adding is 0. So if you add any integer to 0, we always get back that same integer. So that's A star E is equal to A, where A is for any element in that set, and the identity element here, E, is equal to 0. Because 0 does nothing to a set, to an element of that set. Inverses. So this says that for every element in the group, there is an inverse element of that A to the minus 1, so that A star A to the minus 1 is the same as A to the minus 1 star A is equal to the identity element, and in this case A is equal to minus A, because 4 plus minus 4 is always equal to 0, and that's the identity element. Finally, as the last one is associativity. So this basically means it doesn't matter how you group the operation, it gives you the same result. So this here is equivalent to saying 4 plus 3 plus 2. If we put the brackets here, that's the same as 4 plus 3 and then plus 2 at the end. They're both equal to 9. So we can now talk about group theorems, and these are quite useful, and we'll use them later on when we're talking about the Rubik's Cube. So the first one is, if A star C is equal to B star C, then A equals B. So for this example, if we were to say A equals 4 and C equals 3, if we're using integers in addition again, then A star C, so A plus C, so 4 plus 3, if that's equal to B plus C, then we know that A and B are equal. You can obviously see why, right? So B is equal to 4. That's just what the first one's saying. This one here, this one's a little bit more complicated to explain, but we will prove all of these in the next slides. That's just saying that the inverse of A plus B is equal to the inverse of B star the inverse of A. So if we're using this example again, the inverse of 4 plus 3, does anyone know what the inverse of this would be? So the inverse of 7. So what would you add to 7?
Minus 7.
Minus 7. Right, because 7 minus 7 is equal to 0, and that's our identity element. And what we're saying here is this is equal to the inverse of B, minus 3, plus the inverse of A, which is minus 4, and that is equal to minus 7. Right. This will make a bit more sense when we go through the next few slides, hopefully. And the identity element is unique for a complete set. Okay, right. So the first one, prove that if A star C is equal to B star C, then A equals B. So for this one, we can right. So we know that C has an inverse element, let's call it D, where D is equal to the inverse of C, right? And we know that this is going to equal our identity element. That is one of our axioms. That's the identity axiom and the inverse axiom. From here, we can star or multiply, but it's not multiplying, but we can call it multiplying because it looks like multiplying here. So A star C star, we can multiply each side by D, is equal to B star C star D, because we know that this D is the inverse of C, and this here is E, this here is E, so we get that A is equal to B, because multiplying by E does nothing, because it's the identity element. Does that make sense? Okay, and our next one, this is that one from earlier. So, does anyone remember what the inverse axiom said? So the inverse axiom says that for all elements in a group, there is an inverse element so that when you multiply them together or operate them together, you get the inverse element. And that's A to the minus 1. To prove this here, what we can say is, using our inverse axiom, because this is the inverse of that, we can say that A star B star B to the minus 1 star A to the minus 1. This, because that is the inverse of that, means that this is equal to E. Right? Because this is the inverse of that. Now from here, do you remember the associative axiom? That doesn't matter where we put the brackets, so we can move these brackets anywhere we want. So we can say that A star, so A star brackets B star B to the minus 1 star A to the minus 1. This is equal to that. Can anyone tell me anything about what this bracketed part is going to be?
Is that going to be E?
That's right. Right? And because E doesn't do anything, we can forget about that. So this is equal to A star A to the minus 1, which is also equal to E. And so, because we know that this is equal to E, and we've shown that through the associative axiom, this equals E, you know that this is true at the top. Okay. Is that all clear?
Yes.
Okay. Last one. So proving that the identity element of a group is unique, so there's only one identity element E. So first, have you seen proof by contradiction before? Right, so you assume that something different is true, and then you can find the contradiction. That means that the original statement was false. So can anyone give me a statement we can say to begin with that contradicts this statement?
There is more than one identity element in each group.
Perfect. So our first step is assume there is more than one identity element. Okay, we can pretend that there's two, and we'll call these D and E. Okay, right. Our next step, we know that if we multiply an identity element by something else, you get that same element back. So if we say D star E, we know this is equal to, does anyone know what this is equal to?
That'd be DE, because they both.
So this is equal to D, because multiplying by E does nothing, but it's also equal to E, because multiplying by D does nothing. And this here is our contradiction, because we said these are two unique elements, right? So this is our contradiction, and therefore we've proved that this top statement is false, and therefore the identity element of a group is unique. Yeah, does that make sense? Okay. Okay, right. On to the interesting stuff. The Rubik's Cube group. We can represent all the valid sequences of moves we can make on the Rubik's Cube as the set, we call it G, and the operator star, which represents the concatenation of sequences of moves, and that just means putting them together, so doing them in that order that we said. This group is called the Rubik's Cube group, and the set G describes every possible sequence of moves. And this means that we can also describe every single arrangement of the cube. And because each arrangement can be represented as a set of moves it takes to get from that solved cube to that arrangement. And because we've got every possible sequence of cube moves in that group, we can get to every single arrangement of the cube as well. Different sequences of moves that have the same overall result are considered the same element in G. So for example, F squared is considered the same element in G as B, F squared, then BT minus 1. So that's saying that rotating the front face twice is the same as rotating the back face, then the front face twice, then the back face back. So if I show you that quickly, you can see what that looks like. So if we rotate the back face, and then we rotate the front face twice, then we rotate the back face back, then this is the same as just rotating the front face twice. So these two moves here are considered the same thing in G, in our group G. Okay. So the cardinality, that just means the number of elements in the group of the Rubik's Cube group is approximately 4.3 times 10 to the 19 as we saw before. And we can show that this group satisfies the four axioms. So the first one, closure. So rotating cube faces will always give another permutation of the cube, so the group is closed. The identity element is equivalent to not doing anything, because if you don't do anything to a cube, you get the same cube. Inverses, so the inverse of a sequence of moves is that move performed in reverse order and the inverses. So an example of that is to reverse a rotation of the front face and then the back, and then the right face. Does anyone know what the inverse of this would be? Does anyone have a guess?
R minus 1, F minus 1.
Yep. So we're just doing those moves in reverse to undo what we've done. And that. Associativity, so it doesn't matter how we put the brackets, we're still doing the same moves. So it satisfies associativity. Oh. the Rubik's Cube group isn't commutative. So that means that if we were to take two moves, for example R and F, that does not give you the same thing as doing F then R. I can show you that again. So if we move the cube, so if we do F, is that F? If we do F then R, this is not the same as doing R then F. So they give a different result, and so our group isn't commutative. So can anyone give me an example of a group that would be commutative?
With the whole numbers bit one.
Under which operation?
Addition.
Yeah. So that group that we saw before. So this is commutative because adding 4 to 3 is the same as adding 3 to 4. But division wouldn't be because 4 divided by 3 is not equal to 3 divided by 4. Okay. We call these groups non-abelian or non-commutative groups. So we can use this group theory to develop algorithms that will help us solve the cube. Have any of you tried to solve a Rubik's Cube before? Have you seen the algorithms yet? So we can explore commutators and conjugates here that will help us solve the cube. Okay. So if we take two moves, x and y, we can say that the commutator of x and y is the move x, y, x to minus 1 and y to minus 1. And this may look familiar to you if you try solving a Rubik's Cube. So for example, RU, R to minus 1, U to minus 1 is often used in the white cross, yellow cross method. And this up here, this you can also write this as xy and yx to the minus 1 because yx to the minus 1 is equal to the inverse, so x to the minus 1 then y to the minus 1. And so if x and y commute, then xy is equal to yx. So this here is the same as xy times xy times xy to the minus 1 because xy is equal to yx. And this would just be equal to the identity element because of our inverse axiom. So this would be equivalent to not doing anything to the cube. And here you just put that commutators can be thought of as an indication of the extent to which an operation fails to be commutative. So for example, if two moves move a lot of the same cubes, then this commutator will move the cube more than if, let's say, we just had one cube that was affected by both of these moves. Then only that one cube would move as well. Okay, so does anyone know what we can say about moves that would commute? Yeah?
Would it mean that they would result in doing nothing? Or
So if we were to apply our commutator, then yes, that would be equivalent to doing nothing, but do you know anything we can say about those moves without talking about the commutator as well? So if two moves commute, that means that doing them in any order is fine. So doing x then y is the same as doing y then x. Can anyone tell me now anything about these moves x and y if xy is equal to yx? And that means that
It's just the same, right?
so this would mean that they don't affect any of the same cuboids. I'll show you what this means. So if we had, for example, F and B, because F and B don't affect any of the same cubelets, doing F then doing B is the same as doing B and then F. Do you see what I mean? Because they don't affect any of the same cubelets. So that means they commute. But if we had, as we saw before, something like F and R, they affect these cubelets here. So if we do them in the opposite order, they'll result in something different. So if two moves commute, that means that they don't affect any of the same two cubelets. Does that make sense? Yeah? Okay. So we can define a strategy when we're using our commuters, and that is, if they only rotate a few of the same cubelets, then the commutator should also only affect a few cubelets while keeping the rest of the cube the same. Okay, so if it turns out that x and y, the moves x and y, the only cubelet, they only affect one cubelet, then the commutator cycles 3 cubelets without changing the orientation of the rest of the cube. So this is called a 3 cycle, and we'll see an example of this on the next slide, I think. Okay, and the 3 cubelets that are cycled, so A goes to B, B goes to C, C goes to A, and A is a cubelet moved both by x and y. B is a cubelet that y moves to the original position of A, and C is a cubelet that x moves to the original position of A. And we'll see this on the next slide. Okay. So if we say that x is equal to L d L to the minus 1, so if I show you this, okay, so L, then D, then L to the minus 1. This move represents taking the top front left corner away from the top face without affecting the rest of the top face. So it might be a bit clearer if so this is our top left corner here. If I just colour that in. Right. So that is our top left corner. We can watch what happens to it. So L moves that top left corner down. Down brings it across, and then L to the minus 1 brings that face back up to where it was before. So this has taken the top left corner away from the top face without affecting the rest of the top face here. Okay. Okay. So our next, if we call y u, this move only affects the top face of the cube, and we can see that. We see that if we look at the cube again. So then we can move the top face. That doesn't do anything other than move the top face around. And now we can decide which cubelets are A, B, and C. So x and y, the only cubelet that both x and y move is the top front left corner, as we saw. So that is our cubelet A. The move y equals u brings the top front right corner into the position of the left corner. So the top front right corner is now in the position of the top front left corner. So that is our B. And the move x equals L d L to the minus 1 brings the bottom left corner up into the original position of A, and this is our cublet C. And I'll just show you now what that looks like. So, okay. So our cublet A is the top front left corner. So that's here, and x moves the left face then the bottom face, then the left face back up, so that affects these cubes here. And then the top face, the only cubelet that both x and y affect is this one here. Right, so when we move the top face, if we colour this cubelet here, this is our top front right corner. When we rotate the upper face, this moves that cubelet into the top front left position, and that is the original position of A, so that's our cubelet B, the top front right corner, and the move X, if we want to see that the front bottom left corner, we want to see that move up into top front left. So if we colour that in, okay, so that is our front bottom left corner, and if we follow the move X, so L, D, then L to the minus 1, we can see that does indeed move it up into the top front left, where A was before. So those are our cubelets A, B and C. So our commutator is x, y, x to minus 1, y to minus 1. And using our rule earlier that x, y to the minus 1 is equal to y to the minus 1, then x to the minus 1, we can see that the inverse of x is L to the minus 1, the inverse of L to the minus 1 is L, so that goes first. The inverse of D is D to the minus 1, and the inverse of L is L to the minus 1. And the inverse of y is obviously just D to the minus 1. So if we follow this move on our Rubik's Cube, we should see that these cubelets are cycled. So if we colour in the cubelets that we know will be cycled, so that is, I believe that was the top, so that's the front face, so our top front left is this one here, our top front right is this one here, and our front bottom left is this one here. So we should see that these three cubes are cycled. So if we follow our move, so let's move this away. It's just too big. It's slightly too big. There you go. Oh. I think I might just. I'll move this across, hopefully. Okay, now it's disappeared. There you go, there it is. Get the Rubik's Cube back up. Okay. So, if we follow this algorithm here, so L, then D, then L to minus 1, then we do U, then L, then D to the minus 1, then L to the minus 1, and finally U to the minus 1, you can see that these three cubelets have changed, have cycled around. I think that has it? Yeah, I think, yeah. Okay. So everything else in the cube would be in the same position, but just these three cubelets here would have changed position. Okay. Right. Here we go. So we've got one more example of a commutator. This is rotating two corners. So here's our move x. This represents taking the top front left corner away from the top face, rotating it and returning it to the top face. And this mixes up the cubelets in the bottom two layers of the cube. So if I can show you this. Okay. Okay. So this move. Okay. So this moves the top front left corner, this one here. We colour that. We colour it all white. Hopefully we'll be able to see it clearly when it comes up again. There you go. Okay. If we follow this algorithm, so I believe that is our so that is our top front left corner. If we follow this algorithm, it should move away from the top face, rotate it and return it to the top face. So F to the minus 1, D, F, L, D and L to the minus 1. And you can see that this corner is back on the top face, but it will have rotated round. Okay, and you can see all the cubelets on the bottom are all mixed up now. Okay. So y equals u, that moves the top right corner into the top left position again. There you go. Right, we can see what our inverse moves do now. So the inverse of x repairs the damage that we've done using x to the bottom layers of the cube. So that can happen because y, the only cubelets that y moved are the top face, so that doesn't affect the bottom two layers of the cube. So doing x in reverse will repair the damage done to those bottom two layers. And the inverse of y returns the top, front, left and right corners into their positions. And our commutator looks something like this, a lot longer. And if we perform this on the cube, we can see that it does rotate top two front corners. I've got this copied and I've got this ready to paste into the algorithm, so it won't take ages, hopefully. Okay. See if I can get this to work. So if I paste that in here, you should see that the two top front corners rotate. Okay. So I've got that algorithm in here, and if we play this algorithm, it should show these two corners being rotated. So that's just gone past y, and there we go. The rest of the cube stays the same, but it's just these top two front corners that are rotated. Okay, I'm glad that worked. Right, Right, the last part now, conjugates. So this is very similar to what commutators were, but instead, if we have x and z are two moves in the cube, then zx, z to the minus 1. This is the conjugate of x and z. And this represents x being performed on a different set of cubelets. And we'll see what this means here. So if you wanted to flip two edges, but you know an algorithm that flips two other edges, you could define z to move these edges that you want to move into the position that the algorithm moves. So this, and then z and z to the minus 1 will flip these back to where they're meant to be. So if we take an algorithm here, this cycles 3 cubes, the front, bottom, right, front, bottom, left, and top, front, right. If we want to cycle 3 top corners, then we're going to have to bring these 2 corners here to the top. Here we go. So that brings these top, front, left, and top, front, right corners into the front, bottom, right, and front, bottom, left positions. So that when we perform this algorithm, then the right cubes get cycled, but then we can put them back with z to the minus 1 at the end. Does that make sense? Okay. And we can watch this in a minute. So this is our conjugate. So this is the 3 cycle, and this is bringing those corners into the right place and replacing them again at the end. And just quick notes, both y and z are self-inverse. Can anyone guess what that means from here?
Does it mean that if if you times it by itself, you get the identity?
Yeah, and can you see why that makes sense? Because if you rotate twice and you rotate twice again, you've done nothing. Okay. So, right, we can now put this into our Rubik's Cube website, and hopefully this will also give us what we want to see. I'm just copying and pasting that in now. So now this should cycle 3 top corners, so we should see 3 top corners being cycled. And here it's going to put the corners back in position. There we go. These 3 top corners have been cycled now. So that's what our conjugate does. Because if we were to just, I'll tell you as well actually. If we were to get rid of the z on either side and just perform the conjugate, I'll show you what happens. If we were to just have that x, y, x to minus 1, y to minus 1, we would get so if I delete the z and z to minus 1 at the ends, we should see some other corners being cycled, not just top 3. And there we go. So instead of these 2 being cycled, these 2 have been cycled instead. So if we wanted to cycle these top 3 corners, we have to do the f squared at the beginning to get these 2 positions. these two corner cubelets into the top. But if we do that at the end, you can see that it's messed up these bottom two layers. So we have to do that at the start and reverse it at the end again. Okay. Right. So commutators and conjugates, many algorithms used to solve the Rubik's Cube are built on these. And there are various algorithms that many advanced Rubik's Cube solvers have committed to memory, and that will speed up the process of solving the cube. And here are a few examples. You can see commutator here. You can see a conjugate here, and the same here. You can see that commutator and that conjugate over there. Thank you for listening. Thank you very much. Did that make sense to you all? Yeah? Are there any questions any of you would like to ask? No? It's great. Thank you very much.